All right, welcome everybody. Today we are talking about low carbon concrete technologies, policy, and the pathway to model code language. Our presenter today is Matt Adams from the New Jersey Institute of Technology. Today you can find the presentation slides and the post-event recording at newconcrete.org. Attendees are in listen-only mode. And you can ask questions via email at a later point at info@newconcrete.org, or we will have a Q&A at the end of this session as well. And you just put your questions in the Q&A section through Zoom. Okay, as with all concrete mixtures, trial batches should be performed to verify concrete properties. Results may vary due to a variety of circumstances, including temperature and mixture components, among other things. You should consult your materials, cement, and concrete professionals for design assistance. Nothing contained herein shall be considered or construed as a warranty or guarantee, either expressed or implied, including any warranty of fitness for a particular purpose. Today's speaker is Matthew P. Adams, PhD, DASHE. Dr. Matt Adams is an associate professor and co-director of the Materials and Structure MatSLab at the New Jersey Institute of Technology in Newark, New Jersey. His research focuses on the sustainability, resiliency, and long-term durability of innovative cement-based materials. He also studies how governmental policies both support and hinder the adoption of sustainable practices in construction. He is a fellow of the American Concrete Institute, where he is currently chairman of ACI 323 Low Carbon Concrete Code Committee and a member of several other committees. He is also a member of ASTM International, where he chairs the subcommittee on testing for strength of concrete. Dr. Adams has received research funding from the Port Authority of New York and New Jersey Department of Transportation, the American Concrete Institute Foundation, and the U.S. Department of Transportation. He received his undergraduate degree from the University of New Hampshire in 2006 and his Master of Science and PhD degrees from Oregon State University in 2012 and 2015, respectively. Thank you, Matt.
Thank you, Carrie. And thank you all for attending today or listening if you weren't at the live seminar. So today, I'm really going to focus more on policy solutions and how well they've worked and moving towards model code language that we're working on at ACI. But I'm going to start talking about a little bit about the technologies that are there, because talking about those really leads to where our barriers to implementation are. And so we're going to sort of move through all of that today. So what is the issue? Really, if you're here, you probably are aware that concrete production is responsible for a significant amount of CO2 emissions. The number that is thrown around is 7 to 8% of global CO2 emissions. Anthropogenic CO2 emissions are from concrete, and that is a substantial portion. And really, the whole building materials and construction industry is generally related to about 11%. So concrete takes up a lot of that. And really, the majority of emissions come from cement and production. That 8% number is maybe a little bit out of date. We've done a lot in the past decade to really try to improve. So it's probably time for us to try to update that number and see where we still are. But it likely is still a large amount. So if we take a look, though, even though concrete's 8% of that total carbon emissions, in terms of relationships to other building materials, concrete has a relatively low embodied carbon on a per unit basis. It's much lower than some of our other building materials. And so, with that being the case, oftentimes I get asked the question, why are we so concerned about concrete? Well, we produce concrete at a massive scale. We produce it at a much more massive scale than anything else that we produce in the world. In the US, we make over 400 million cubic yards of it a year. And just to put that into context, that is not one Hoover Dam, it's not 2 Hoover Dams, it's not 10 Hoover Dams, it is 615 Hoover Dams. So that's a lot of Hoover Dams that we construct just in the US alone. And the US is certainly not the country that is doing the most new construction in the world, right? So we are just a part of that number. It's globally, it's a huge number, the amount of concrete that we make. And so because of that, all of the carbon that is produced, even though it's relatively small on the per unit basis, it adds up pretty quickly. So where's all of that carbon coming from? Greater than about 90% in most cases of the embodied carbon in a pure Portland cement mixture is really from the cement production. And this can be broken down into the quarrying, transport, and grinding processes, the process emissions, which are chemical emissions that come from the process of making the cement, and then thermal emissions, which are really associated with burning the fuel to heat up the kiln for making cement. So you can see from this graph from Chatham House that more than 50% of the total CO2 that we're producing when we make cement is coming from that chemical process. So at the moment, it's not really avoidable. So if you're familiar with cement production, we make cement in a large rotating kiln, and we heat that cement up to about 1400, 1500 degrees Celsius. And at the end, we get clinker that we crush down with gypsum to form Portland cement. During that process, we release quite a bit of CO2. First, like we said, about 40% is from the burning of the fuel source to heat the kiln. We've done a lot of work to make that more efficient, but you still are burning, at the end of the day, you're still burning quite a bit of fossil fuels. But really the main source is from the calcination of the limestone. Limestone is a raw material we put in so that we can get calcium oxide, which is a main component of cement. And when you burn that calcium carbonate or the limestone, when you heat it up, it drives off CO2, so you get the calcium oxide. And right now, in most cases, that CO2 is just being released to the atmosphere. And so that is a huge source of CO2 coming from cement production. There are a number of technologies for reducing the CO2 related to concrete. First options are sequestering the CO2 into concrete. So these are technologies like what is being sold by Carbon Cure and Solidia, where you're actually putting CO2 into the concrete and locking it away. I'm not going to touch too much on that today. You can reduce your total Portland cement content and your total cementitious materials content. We can try to reduce or capture CO2 production at the source. And then we can also try to minimize the carbon in our non-cementitious materials, so minimizing carbon associated with the aggregates and other processes in the concrete production process. So how do we reduce our cement content? You know, the amount of cement in a concrete mixture is about 7 to 15%. If we can try to step away a bit from using all Portland cement, which a lot of people have started to do, and think of it as just total cementitious materials, we can start to include things that have much lower embodied carbon. So ground limestone, common supplementary cementitious materials, though we know that there are potential access issues for fly ash and slag on the horizon. And then we have newer SCMs that are coming onto the market, like ground glass pozzolans and calcine clays. Not going to get too deep into what these are, but you know, there are many options for trying to reduce the total amount of cement in your system. We can also try to reduce the overall cement content by improving aggregate gradation. So essentially packing more aggregates into the space means you have to fill less of that space with cement. This is still a technology that is being developed in terms of what is the best way to calculate that packing. How do you actually blend your aggregates? What's the cost associated with it? How do concrete plants actually do this at scale? Right now, it's been done quite a bit in lab creep, but getting the concrete plants up to the next level is kind of another stage. But really the most important thing for us is not to over design our concrete. Concrete strength is not a strongman competition. It's not about who is the strongest and the best. It's about making the concrete that you need for your particular application, right? We know that we can dump lots and lots of cement into a system, get pretty high strengths, get higher early strengths with that. But we don't really need that. You can get great strengths with more careful design. You can get everyday strength, 4,000, 5,000 PSI with fairly low cement contents. So just trying to be more cognizant of the way we design our systems will really help. Another tool that is being examined is reducing or capturing CO2 at the source. Modern cement plants are pretty efficient in terms of energy efficiency, heat capture, et cetera. There's always improvements to be made, but we've done a lot of work in that space. But in terms of trying to capture the CO2 that's coming out of the kiln, particularly from the breakdown of the limestone, there's technologies that are in development, but likely retrofitting plants is going to be incredibly costly, and that cost will get passed down to the consumer in some way. So that, there's a limitation to how much that can happen based off of how much people are willing to pay for the cement. And then, you can try to minimize CO2 and other components such as the aggregate, but really these have minimal impacts on the overall CO2 in the system, because the amount of CO2 associated with making aggregates is relatively low in the first place. Like I said, about 90% of the CO2 embodied in concrete is really associated with the cement content. So focusing on how to reduce cement content and how to improve the other materials that you're using in that system will really get you better gains. So we have all of these technologies. What's the barrier to implementation? Why have we not used these more effectively? First, there's always a fear of cost. Anytime we're looking at something new, people are worried about how much it's going to cost. And I don't, not everything that we do has an increased cost with it. Some of the technologies do have increased costs associated with them, but not all of them do, particularly ones that we've been using for a while. The cost is really not significantly different. And so we have the ability to make low carbon concrete without significantly increasing the cost. And this has been shown by many agencies that have started to use low carbon concrete. We do have issues with knowledge transfer. The good example that I always like to put out there is there was a town in upstate New York that wanted to start using low carbon concrete, and they were referring to it as green concrete. They went to their local concrete plant, and the concrete plant said, "Why would you want to dye your concrete green?" Right. So there are these miscommunications and misinformation. And then there's just folks who don't have the base knowledge. And so ACI, NEU, educators, we can start to develop more easy to access knowledge transfer tools to get that information out. Space and capital at concrete plants is a real difficulty. A lot of concrete plants, particularly in urban environments, sit on very small parcels of land. So when you start asking them to introduce new materials, it's not just about learning what that material can do and how to use it, but where do you put it? Do they have space for another silo of cementitious materials? Do they have space for a third size range of aggregates? They don't always have that space. And so we need to provide capital to expand or come up with new methods for storage. Liability is always a concern, particularly in construction when we're moving into new materials. For low carbon concrete, there isn't a lot of national level guidance. We don't have a code, a national level model building code. So when it comes to best practices, a lot of times contractors are nervous to implement things because they don't have those sort of national level proven technologies to fall back on, and they don't want to take on the risk themselves in case something does end up going wrong. And then political will is always an issue. The rest of these, particularly when we're talking about public projects, the rest of these issues can really be solved with political will and putting in the right policies and funding. But you need to have legislators and policymakers who are interested in this and want to create more sustainable concrete. But then also, that are willing to look at all of these barriers holistically and how do you drive them? How do you keep all of the implementation costs off of the contractors, off of the concrete producers, and try to make it a real community effort. So those are some of the main barriers to implementation. We've seen a lot of policies start to get implemented around the country. Some of them have been more successful than others. So I want to take a little bit of time to talk about each of the different policies, or some of the main policies that have been put out. I won't say that this is all inclusive, because there's new stuff coming out every day, every week, from different jurisdictions, and it's really difficult to keep tabs on all of it. But some of the first policy that came out, and I start this by saying good policy can save the world, bad policy is just ineffective, right? We saw a lot of policy work start at the local and state level, really with a lot of non-mandatory resolutions. So when you're talking about a resolution, it's usually some legislative group standing up and essentially making a statement or saying, we think this should happen, but there's no requirement behind it. There's no enforcement. There's no incentives. It's just, hey, we think you should do this. And some of the first low carbon concrete policies that came out really focused on promoting the use of carbon storage in concrete. So, the use of things like carbon cure or solidia, et cetera. And these really the first few that came out were from the state of Hawaii, the city of Austin, and the US Conference of Mayors also made a resolution on this. These policies were really mainly kind of pushed and lobbied for by some of the private companies. The resolutions weren't bad necessarily. They just didn't really have any teeth to them. So there wasn't, they didn't really get that effective. And for a lot of these technologies, you really need special equipment. So even if a city says we want this, was it available nearby? That was a problem. So this is where we really start to see that, these resolutions are good-natured, kind of get people interested in the idea, but they're really not moving us forward. There were some resolutions that were taken that were very successful. One example is one that was put together by the village of Hastings-on-Hudson. So if you're unfamiliar with New York sort of jurisdictions, villages are basically sub-city level government. So it's the village of Hastings is part of a larger city area up in upstate New York. And they put together a resolution that ended up being very effective. They were able to have a lot of projects that have come out of this that have utilized lower carbon concrete systems, both at, they started at the very small scale with a probably 25-foot long retaining wall. That was their pilot project. They've now scaled up. They have it in an elementary school. They did a massive sidewalk project. They have a number, basically all new concrete being put in the city is following low carbon concrete technologies. it's also expanded out of Hastings to most of the surrounding villages and towns, and starting to get traction sort of through a broader region within New York. And so this resolution was pretty, we would say, is pretty successful because it had the impact of accomplishing the goal of having more low carbon concrete, not just in that town, but in the area. And so there were a number of reasons that we could link back to for this resolution being very successful. First, it was technology agnostic. So while they listed in the resolution different types of technologies that could be utilized, they didn't limit them, and they basically said, however you can get to lower carbon concrete, that's great, as long as you're not affecting health safety or life safety requirements. They also engaged a lot of community stakeholders while they were developing the resolution. So it wasn't just a city councilor wrote this and put it up and they voted on it, right? They talked to the town engineers, they talked to the local concrete companies, they talked to the local contractors that they used regularly, and said, you know, how do we do this? Can you do this? Is it possible? What is the town engineer going to need to do? What extra are they going to have to take on? Extra work, extra burden to understand this. And then they had city leadership involved both in the development and implementation. So they had buy-in from people within the city that work there to say, yes, we're interested in this. Yes, we want to help implement this, and we'll take this on to do that. And the city was also willing to absorb risk. And so they were willing to say, look, you know what, if these first couple of projects don't perform well, okay, we'll fix them, and we'll move on from there. Of course, that hasn't been a problem. We engineers know that you can make great quality concrete with lower carbon, lower embodied carbon. And then the last thing that has really led to this expanding is that the resolution actually has a resolution that the city should educate the community and other communities. And so they backed that up by sending the mayor and council members around the state of New York to present on this resolution and talk about why it was successful and how to actually implement a resolution like this. And so a lot of other groups in the state have started to implement it. So this was a relatively successful resolution. Again, it didn't have a lot of teeth to it, but because the community was dedicated to it, it made a relatively large impact on a very small village. The next group of policies that kind of came out that we can kind of move up to the next level is global warming potential declaration policies. So the idea behind this was really that sunlight is the best disinfectant. So no limits on the global warming potential or the carbon embodied carbon emissions of your concrete. Just all of these, all of certain types of concrete mixtures need to declare their global warming potential. So this started with the state of Colorado and the city of Portland. It's moved on to other areas. The first round of the Cal Green standards for low carbon concrete is really just declaration. As that kind of continues to move forward, they will move forward with limits. But, you know, and it's likely that Colorado and Portland may put limits in the future as well. But the idea here really is just to get people to start saying how much embodied carbon is in their concrete and get that out publicly, have it be a part of the process. And this is really good because even just getting used to how to calculate this is a barrier for a lot of people. So by saying you have to do it, it starts to become a part of the process. Interestingly, there is one jurisdiction, the state of New Jersey, where I work, where they actually developed a law that provides tax incentive to contractors. So in New Jersey, I'm not sure exactly when the law goes into effect, but it was signed earlier this year, based off of how much reduction over a baseline mixture the contractor is able to produce, they can get up to 8% of their total cost of the contract as a tax incentive, as a write-off from the state. So this, we'll see how effective this is. It hasn't really been out there long enough to determine how much it's going to be used. This is an optional item, so basically contractors can choose to do this as a part of the bid and see what happens. And we'll see what happens with the actual cost of the contracts and how that gets impacted, and how many people actually take up the state on this offer. But it'll be really interesting. This is really the first of its kind for lower carbon concrete mixtures. The next ones are really starting to set limits on the total global warming potential allowed in embodied carbon concrete, and also limits on the total amount of Portland cement and in a system. So the first group to really implement this was Marin County in California, so just north of San Francisco. And so for all concrete projects, public concrete projects that are in unincorporated areas of Marin County, they have limits on either the total cement content or the total global warming potential. And those limits are based on concrete strength. So the stronger the concrete is, the higher the allowance of cement or global warming potential is. Port Authority of New York and New Jersey, they also just released a new specification that was both limits cement content and requires calculations of GWP. Those limits really were based on internal studies of global warming potential. So for Marin County, they did a study of concrete made locally, determined the global warming potential of that, and set their limits based on that. For Port Authority, their limits were set based on their own internal data. And so they came up with what those limits could be, what they felt was going to be achievable. And now those are requirements for all concrete in the state. It's not really, or all concrete in those jurisdictions. It's not really a choice for the contractors. They need to meet the requirements. Most of them, or both of them, do have carve-outs for high strength concrete and high early strength concrete. But because they are the owners in both of these cases, they get to really control over when those carve-outs can be used. The state of New York just released their new limits. So I believe it was on Tuesday that they released this information. So they are following a similar ideas, Marin County and the Port Authority. So they're limiting the total global warming potential based on the strength of the concrete. And the limit that they have chosen is 150% of the NRMCA regional average concrete global warming potential for the Northeast region. So if you're unfamiliar with this, the National Ready Mix Concrete Association has come up with averages for the global warming potential for concrete based on regional averages in the US. This is a really great benchmarking tool that they have developed. There are some limitations to it. The data while it is very good, is somewhat limited. And so while this is a great start, we have a lot of work to do in this area of trying to really determine what those benchmarks, what those baselines should be. This was what is out right now is kind of a first pass and is based off of limited data sets. In the world of concrete, we do have what I like to refer to as a data problem, in that it's not that we have too much data, it's that we really don't have enough well-organized and easily accessible data. So we need to really step up in the community in data sharing so that we can get really good answers and information. But for right now, the state of New York has set that limit. Your concrete can have up to 150% of the regional average for global warming potential for the Northeast. So likely that number will reduce over time, but right now that's where it's set. At the national level here in the US, both the Inflation Reduction Act of 2002 and General Services Administration have started to set requirements for low carbon building materials. The Inflation Reduction Act work is being overseen by the EPA, and what those requirements are and how to meet them is still sort of in flux. How do you actually calculate your GWP? What limits should you use? What makes a low carbon building material hasn't really been determined yet. So there's still a lot of work to be done there, but that is coming, and they are in the process of figuring that out. And so what all of this comes down to is that there has been a lot of policy put together, and it's kind of all over the place. There's different ways of calculating the GWP. There's different benchmarks that have been set. There's been different limits that have been set. There's been different ways to incentivize or the use of the material. And really, progress is messy. Moving forward is messy. Trying to get there is messy. But in that middle space is really where success is born. By seeing all of these programs, we're able to understand what can be done and what is successful. And so out of this, we are at a point where we really need to develop national level building code and national level model building code language and tools for getting us to low carbon concrete that jurisdictions can adopt, and we can have sort of a consistent way of calculating global warming potential and calculating limits across the US and really around the world. So that national level model code guidance is needed. There's a few things that we really need to sort of decide. How do you determine the global warming potential of the concrete of your building? What are the best practices there? What's the best way to do this? How do you calculate it? What limits do we set? What should be the limit on the global warming potential? What benchmarks should be used? How do you calculate those benchmarks? These need to be determined. And then how do, the big question that comes up is, how do these limits interact with life safety code? The question that I have seen come up most often when talking with legislators and contractors is, how do I make sure that I meet these requirements without impacting life safety? How do I make sure that my building isn't going to fall down? Engineers that work in this space know it's not that hard to meet life safety requirements while getting to low carbon concrete. But folks who are not well educated in this area have a lot of doubts. And basically what we know is that you follow the life safety code, that comes first, and then you can implement the provisions of low carbon concrete within that. Where you have a conflict, the life safety code is going to control. That is always comes first. And so to try to determine all of this, try to come up with a code that meets these questions and myriad other ones that fall under each of these headings, ACI Code Committee 323 is here. We're here to try to save the day. This committee has been put together recently. Our first meeting was in April of this year, to try to make sense of everything that's happening nationally and come up with model code language, right? So like I said, we first met in April. We have a very strong cross-section of experts in low carbon concrete, concrete materials, carbon limits, legislation and policy and code writing. And right now we are on track to release this code likely somewhere in mid-2024. So we are hoping to have a fully usable model building code for low carbon concrete next year. We are on track for that. We have some draft language that we are in the process of polishing up and cleaning up, and then it will go for approval to the various groups above our committee that need to approve it. But really, how we develop that code is, it took us some time and a lot of conversations. So when you go to develop a low carbon concrete code, there's a path that the code needs to go through to actually get those answers. So first you need to come up with the categories of construction. So how are you going to break all of the construction that's made with concrete in the world into different groups? Second, what is the path to compliance? So what path do you walk down in terms of calculations to meet those goals and figure out if your system is above or below the limit? And then finally, what is the limit that needs to be met? When it comes to low carbon concrete, this can look something like breaking the categories into strength, different concrete strength levels, setting prescriptive limits on the cement content, say, that can be a path to compliance. So you can only use a certain amount of cement in your mixture. And then that limit is, say, 500 pounds per cubic yard. So this is a path that has been used. This is essentially what Marin County has implemented. We know that this is not necessarily the best path because concrete strength is not necessarily related to GWP. You don't always get a higher global warming potential when you have a higher strength concrete. And so it's not always the best path to go down, though right now, in terms of data, that's really where we have a lot of data. We also know that setting prescriptive limitations is not the best way to fuel innovation. Telling people exactly how to make a concrete mixture is not the best way. You really want to have a performance expectation rather than a prescriptive limitation. So we need to tell our concrete contractors how the concrete should perform and not exactly how to make the concrete, because every concrete is different, every location is different, materials are different. We want to have the experts who design the concrete mixtures and use those materials every day. We want them to use their knowledge to develop the best concrete mixture that meets our performance requirements. And so with that, we want to set performance requirements for low carbon performance rather than limiting any one particular item in a concrete mixture. So really the way that we're moving is to really look at type and size of construction as our categories, and then a path for determining the global warming potential of your mixtures, and then putting limits on the total global warming potential based on how big your construction project is. And so this is the path that is most likely to be the most effective when creating a code. So for our code, the likely system, and I say likely because we haven't finished it yet, but this is, what we have, through research and discussion that we've come up with, is sort of being what is likely to work well. In terms of categories of construction, we're breaking things down into types, so bridges, pavements, buildings, etc., and then how large of a construction project is it. So based off of the size of your construction project, you will have different limitations set forward. The path to compliance for this is to determine the global warming potential for each mixture. So doing that, the easiest way to do that is by getting environmental product declarations created for each of your concrete mixtures. And so moving forward, we're hoping that more and more concrete companies start to avail themselves of developing EPDs so that they can truly know what the global warming potential, the embodied carbon of their concrete mixtures is. And then once you have that for each mixture, you can essentially create a weighted global warming potential for all of the concrete in your project, right? So even though you might have some concrete with a high global warming potential because you need, high early strength for, removing formwork for one area of the project, you might also have some concrete for a sidewalk that has a relatively low global warming potential. And so by weighting those together, you can get, a good an average GWP for the whole project that will meet your limits. And then setting our limits will be based right now on the NRMCA regional global warming potential benchmarks. So we are having our benchmark GWP. So the GWP that we want you to compare against will be those NRMCA regional averages. But within the code, jurisdictions that implement this code can also use localized data similar to what Marin County and the Port Authority have done, right? So you can actually go and create your own regional benchmarks and use those. That would be best because each region has, different requirements for where they can get their materials from and transportation costs and what materials are actually available. But if you don't have the resources to do that, here we've got the NRMCA regional benchmarks, which are available, and hopefully those will just continue to improve in quality and knowledge, and then we'll set a limit on how much of that benchmark you can meet. We have some ideas for what the limit will be. I don't want to talk about that until we finalize the code, but we're getting there. So our new code that we'll be developing, or that we are developing, is likely to follow this process. It's actually, we think of a code, we might think of 318, which is, hundreds of pages. This is going to be right now a 25-page code. There are lots of things that need to be considered for sustainable and low carbon concrete, like whole building life cycle analysis, what about recycled materials, et cetera. Some of that stuff is not necessarily relevant to the low carbon code, but likely in the future, we want to see some of these other ideas be put into the code. But right now we're looking at a really focused content of setting global warming potential limits for the embodied carbon of a concrete mixture. So not looking at whole building life cycle, not looking at the whole life cycle, just, for your mixtures and what should you have at that initial stage. So with that, that's really the end of my presentation. We're getting there. Hopefully next time I can come back to NEU and give a full presentation on how this code works. And hopefully that will be next year sometime. But just to kind of revisit what we went over today, hopefully from this you can sort of describe the state of low carbon concrete policy in the US, discuss the need for model building code language. We really need to have some model language that people can use, because right now we're a little bit all over the place. And then describe the current state of technology for low carbon concrete. There's lots of options out there for us to use. And before I say thank you and walk away, I just want to acknowledge my research group at NJIT, along with Dr. Bandelt and a whole group of PhD and master's students and undergrads who have helped complete a lot of the technical research that we're working on. My partnership with the Rockefeller Institute for Government, and then the ACI 323 committee members who have really put together this code. So Dr. Andrea Shocker, who is ACI staff, who's been our staff secretary. She's done a lot of great work to help us out. Dr. Chris Ferraro, who's our vice chair, who's helped make sure the meetings go smoothly. And then our committee members who have just been amazing at staying on task and getting us where we want to be. And then ACI and NEU staff who have helped us on the back end, and then all of the different groups that have funded my research over the years. So I just want to acknowledge all of them. And with that, I'll say thank you, and I'm open to taking any questions.
If you have any questions, please enter them on the Q&A. Or otherwise, you can email them to us at info@newconcrete.org. And we can forward them to Matt to answer later.
Question from somebody was, are benchmarks based on regular type 1 or type 2, 5, or blended cements as well? The regional benchmarks, I believe, are based off of a slightly blended system of type 1 and a certain percentage of SCM. I can't remember exactly what. If you go to the NRMCA benchmark report, it tells you all of that information. Like I said, this effort from NRMCA was a good first step. It's not, we sort of need to gather more data to really understand where this is. But it was a good first step. But I believe the regional ones are based off of some blended cement systems. The national average ones are slightly different. But yeah, the best place to get that question answered is from the NRMCA report itself, which is available online for free. Well, thank you everybody for coming and listening to me talk about concrete policy.
Thank you, Matt, for coming. We appreciate it. Great presentation. And thank you all. Please come to our website so you can view the presentation again. And as you said, please contact us at info@newconcrete.org for any questions you have. Thank you.